initiate the visual rendering sequence and strip away the external aluminum skin of the A-10 Thunderbolt II. Forget the conventional myth of an airplane equipped with a mounted gun. Isolate the structural framework and observe the raw engineering truth. What you are looking at is a colossal self-contained rotary cannon that simply had wings and twin engines bolted onto its chassis. Execute a Boolean cross-section cut through the nose assembly. Peel back the protective layers to expose the 38mm thick titanium bathtub, a 540 kilogram armored shell designed exclusively to shield the pilot from direct anti-aircraft fire. Render this titanium armor transparent to reveal the absolute mechanical dominance of the GAU-8 Avenger. This is not a mere weapon. Extract the entire gun and feed system from the airframe. Weighing in at 1,828 kilograms and measuring exactly 5.8 meters in total length, this monstrous rotary mechanism is physically equivalent to stuffing a classic Volkswagen Beetle directly into the nose of a fighter jet. Zoom in on the intricate internal architecture of the firing mechanism. Isolate the primary drive system. This cannon does not rely on a conventional gas-operated mechanism. Activate the dual 77 horsepower hydraulic motors. These high-pressure hydraulic drives generate an immense rotational torque, directly powering a highly complex linkless feed system. Observe the massive ammunition drums situated deep within the fuselage, capable of holding 1,174 rounds. As the hydraulic pressure surges, the drum begins its relentless rotation. The mechanical synchronization here must be flawless. Track the movement of individual rounds as they are pulled from the drum and forced down the feed chute. Accelerate the 7 precision-machined 30mm barrels. The immense hydraulic torque violently spins this barrel cluster, pushing the mechanical limits of the steel alloy to achieve an extreme maximum firing rate. At peak rotation, the GAU-8 vomits an apocalyptic 3,900 rounds per minute. Translate that into raw physical output. That equates to exactly 65 massive projectiles exiting the muzzle and tearing through the atmosphere every single second, creating an acoustic shockwave that sounds less like gunfire and more like a catastrophic fabric tear in the sky. Now, execute a high-speed probe lens macro shot and perform a longitudinal cross-section cut on a single PGU-14/B armor-piercing incendiary projectile. Strip away the lightweight aluminum outer casing. Penetrate deeper to inspect the lethal core. This is a 300-gram depleted uranium penetrator. Analyze the material density. Depleted uranium is extremely heavy, possessing a density 1.6 times greater than solid lead. Calculate the sheer kinetic energy transfer during a combat engagement. Upon ignition of the propellant charge, this dense metal spear is violently ejected from the barrel. Track the trajectory as it breaks the sound barrier, achieving a supersonic muzzle velocity of 1,013 meters per second. Project this flight path onto a virtual battlefield. Imagine this hypervelocity projectile striking the side profile of a Soviet-era T-62 main battle tank from a standoff distance of 1,200 meters. The sheer kinetic force does not just dent the metal. Upon impact, the extreme pressure and friction instantly liquefy the 100mm thick-rolled homogeneous armor. The depleted uranium core exhibits a pyrophoric effect, meaning it spontaneously ignites upon shattering against the hardened steel, spraying a localized inferno of molten metal and superheated shrapnel into the enclosed crew compartment. It operates exactly like a hypervelocity plasma blowtorch, effortlessly slicing through a block of frozen butter. reassemble the external structural grid, and pan the camera outward to analyze the overall mechanical axis of the aircraft. The extreme kinetic output required to unleash this level of destruction generates a terrifying mechanical paradox. Calculate the recoil force. When the GAU-8 Avenger is firing at full capacity, it generates an instantaneous recoil force exceeding 10,000 pounds. This creates a severe engineering nightmare. Highlight the central axis of the airframe. If the specific barrel that is actively discharging a round is even slightly misaligned from the exact center of gravity of the aircraft, that 10,000-pound asymmetrical recoil force will generate a catastrophic yaw torque. In a real-world aerodynamic environment, this violent twisting motion would literally tear the aluminum airframe apart mid-flight, instantly ripping the wings from the fuselage under the immense physical stress. Shift the camera perspective to the underside of the nose section and highlight the landing gear. To perfectly align the firing barrel directly onto the aircraft centerline, aerospace engineers were forced to execute a bizarre physical compromise. Notice how the active firing barrel is always positioned exactly at the 9 o'clock slot. To make room for this massive barrel right in the dead center of the jet, the entire front landing gear mechanism had to be physically offset to the right side of the aircraft. This asymmetrical anatomy is a direct testament to the raw, uncompromising dominance of the weapon over the machine that carries it. Every single rivet, every hydraulic line, and every structural rib of the A-10 Thunderbolt II bends to the absolute physical will of the GAU-8 Avenger. Isolate the barrel cluster once again and activate the thermal imaging overlay. Friction is the ultimate enemy here. When 65 rounds of depleted uranium are pushed through the rifling every second, the mechanical friction generates extreme thermal spikes. Focus on the steel alloy construction of the barrels. Without proper heat dissipation, these barrels would warp, melt, and catastrophically detonate within seconds of a continuous trigger pull. Observe the open-air design of the barrel housing. Engineers deliberately left the forward section of the weapon exposed to the oncoming supersonic airstream. This forces a massive volume of sub-zero atmospheric air directly over the rotating barrels, utilizing extreme aerodynamic cooling to prevent a critical thermal meltdown. Now trace the path of the empty casings. In a standard fighter jet, expelling hundreds of heavy brass casings out of the bottom of the aircraft at high speed could cause fatal structural damage if they strike the fuselage or get sucked into an engine intake. Highlight the return chute mechanism. The GAU-8 employs a closed-loop system. The empty casings, still searing hot from the detonation, are mechanically forced back up a secondary chute and violently shoved back into the massive ammunition drum. This intricate mechanical ballet not only prevents self-inflicted aerodynamic damage, but also precisely maintains the delicate center of gravity. If the aircraft suddenly lost over 1,000 kilograms of mass by dropping the casings, the extreme shift in weight distribution would immediately violently pitch the nose of the aircraft upwards, inducing an unrecoverable aerodynamic stall. The engineering precision required to cycle these massive rounds in a continuous loop under the extreme gravitational pressures of combat maneuvering is nothing short of a mechanical miracle. Now place this massive flying cannon into a highly volatile combat aerodynamic environment. We must address a terrifying physical paradox between thrust and recoil. Isolate the twin General Electric TF-34-GE-100 turbofan engines mounted high on the rear fuselage. Zoom in on the titanium compressor blades spinning at over 17,000 revolutions per minute. When operating at maximum capacity, these two bypass engines suck in massive volumes of atmospheric air, compress it, mix it with jet fuel, and ignite it to generate a combined forward thrust of approximately 18,000 pounds. Now, recalculate the mechanical counterforce generated at the nose. As previously established, pulling the trigger on the GAU-8 Avenger unleashes an instantaneous recoil force of over 10,000 pounds in the exact opposite direction. This means the sheer violent recoil of the cannon actually neutralizes more than 50% of the aircraft's entire forward momentum in a fraction of a second. Imagine driving a heavy commercial truck down a highway at 560 kilometers per hour and suddenly slamming a massive steel emergency brake. The aircraft literally violently decelerates mid-air during a gun run. The pilot is forcefully thrown forward against the harness, subjected to immense negative gravitational forces while suspended in a highly hostile anti-aircraft zone. But the kinetic deceleration is not the fatal design flaw. Zoom in on the muzzle of the cannon during a simulated firing sequence in the upper atmosphere. The detonation of the propellant charge inside the casings does not just expel the heavy uranium core. It simultaneously creates a massive, rapidly expanding cloud of superheated, oxygen-deprived gun gas, heavily saturated with unburnt carbon, sulfur, and lead vapor. Analyze the aerodynamic flow of this toxic vapor across the aluminum skin of the fuselage. Due to the placement of the cannon at the extreme front and the turbofans at the rear, this dense, suffocating cloud of combustion byproducts is caught in the supersonic slipstream and violently sucked directly into the engine intakes. The TF-34 turbofan engines require a constant, massive intake of clean atmospheric oxygen to maintain the delicate, continuous internal combustion within the core. When this wall of oxygen-starved, chemically dense gun gas floods the first stage compressor blades, it aggressively chokes the airflow. It violently suffocates the primary combustion chamber. The extreme lack of oxygen causes an immediate and catastrophic compressor stall. The engine experiences a violent internal backfire, immediately followed by a complete flameout, effectively turning a heavily armored 14-ton war machine into an unpowered falling brick directly over enemy territory. To prevent this mechanical suicide, aerospace engineers had to implement a desperate but brilliant mechanical patch. Render the twin turbofan engine casings transparent to observe the inner core. They hardwired a continuous high-voltage ignition system directly to the weapons trigger in the cockpit. The exact millisecond the pilot squeezes the trigger to unleash the cannon, the engine igniters automatically begin firing continuously, sparking like a high-intensity welding torch inside the combustion chamber. If the oxygen-deprived gun gas suffocates the flame, the continuous high-voltage electrical spark instantly reignites the jet fuel. The exact fraction of a second fresh oxygen returns to the intake, preventing a total mechanical stall and keeping the turbine spinning. Furthermore, inspect the extreme tip of the gun barrel. Engineers welded specialized mechanical deflectors, essentially aerodynamic baffles, onto the muzzle. These angled metal plates forcefully manipulate the violent aerodynamic slipstream. As the gas expands, these baffles physically shove the massive cloud of toxic vapor downwards, forcing it to slide under the curved belly of the aircraft, actively redirecting the suffocating smoke away from the high-mounted engine intakes. Put these raw theoretical parameters to the ultimate combat test. During Operation Desert Storm in the winter of 1991, this highly controversial mechanical setup was unleashed upon the sprawling Iraqi armored divisions in the freezing desert landscape. The results were a display of unprecedented mechanical violence. Let us analyze a specific combat profile. Operating at dangerously low altitudes under the cover of darkness, utilizing infrared targeting pods to detect the thermal signatures of idling diesel engines, the A-10 lined up its attack vectors. The precise combination of the aircraft's low-speed loitering capability and the GAU-8's hypervelocity depleted uranium rounds proved devastating. When the uranium core struck the heavy cast steel turret of a T-72 main battle tank, the kinetic transfer was absolute. The pyrophoric uranium shattered, igniting a localized plasma inferno that instantly detonated the tank's internal ammunition carousel. The resulting internal explosion generated a catastrophic overpressure wave that violently blew the massive multi-ton turret completely off the chassis, turning heavily armored columns into shredded, burning scrap metal scattered across the freezing desert floor. By the end of the conflict, the Thunderbolt had systematically dismantled over 900 main battle tanks and thousands of other armored vehicles. Despite its terrifying aerodynamic flaws and the extreme physical paradoxes it creates during flight, the A-10 Thunderbolt II stands as a testament to the absolute triumph of raw mechanical brutality over elegant aerospace design. It is a machine built around a single, uncompromising purpose: total physical annihilation of enemy armor. If you were sitting strapped inside that titanium bathtub, suspended thousands of feet over a chaotic, fire-lit battlefield, would you trust a machine that constantly tries to rip its own engines apart just to unleash hell on the enemy? Do not forget to subscribe to DEFUNCT and drop a comment below sharing your technical thoughts on this monstrous piece of military engineering.